The final topic we want to touch on here is the idea of what's called structure-acidity relationships. So we've talked about acid strength, the fact that we have strong acids and weak acids, and this idea of that they react with water and how that informs how complete their reaction is, and that we could even have relative strengths within weak acids, stronger, weaker, weak acids. And so what we want to talk about now is how we can make or predictions, or at least understand why certain molecules are strong acids or weak acids based on the molecule itself, based on what atoms are in the molecule, what the molecule looks like, that kind of stuff. And when we're understanding acid strength, really it's based around two similar but distinct factors. And we can base it kind of off the idea of an equilibrium and where the equilibrium lies. So the first idea would be from the reactant side of the acid molecule. If we want to think about, kind of the idea of what an acid does, acids donate H+, so a molecule with a weak bond to a hydrogen atom would be a relatively good acid. So the first thing we want to look at is the acid molecule, is it a weak covalent bond holding that hydrogen on the molecule, so would it therefore be easier to donate the H+. At the same time, in order for this, if we're talking about a strong acid, we say that the equilibrium lies to the product side. So that could also happen because A-, right, the conjugate, is relatively weak as a base. And so if it is a weak conjugate base, basically then it would be the original acid would be stronger. And so this would basically mean that, like, a base is something that takes up H+. So is that base not really that desperate to gain H+? Is it stable as an H+, an A-? So would that mean that it doesn't really, actively grabbing onto H+? So is this base that we make more stable, right? This is just kind of stable as it is. It's not going to react with something else to take H+. So it's weak as a base, leading to this being a stronger acid. So one of the things that we want to think about then is how acids that are basically just hydrogens attached to atoms, how they change. And we can relate that to periodic table trends. So acid strength increases down a group. So if we look at, say, the halogens, so fluorine, chlorine, bromine, iodine, as you go down the group, basically you get to stronger acids. So this is true for any group on the periodic table. If you have atoms on the bottom of the group bonded to hydrogen, they are stronger acids than anything at the top of the group. And this is related to atomic size. So the first thing we can look at is, again, from the acid perspective. And so as you go down the group, if we think about these acids, hydrogen is staying the exact same size, right? All of these hydrogen atoms are the same size, but the other atom is changing in size. And basically what happens is we can see that they are increasing in size. And because they are bigger, what that means is that the sharing of electrons in the bond doesn't happen as efficiently. This iodine atom is massive, especially relative to the hydrogen atom that it's sharing electrons with. Because they are so different in size, it is more difficult for them to share electrons, meaning that this is a weaker bond. If we think about these halogens, we know that HF is the only one among these that's weak, and it's because these two atoms right here are very similar in size. Fluorine's pretty small, hydrogen's small as well, so they have really good overlap of their orbitals. The bond is really strong there. You have very, very nice sharing of electrons there. Also, if we look from the anion perspective, for a larger anion, there is less concentrated negative charge. We know that in creating these conjugate bases, they all have the same -1 charge, right? So there is one extra electron on each of these ions. Iodide is very large, meaning that that one electron can spread out more, right? It is one additional electron among many, so it doesn't make it as relatively unstable, whereas fluorine only has 9 electrons because it's small, adding in that 10th electron to turn it into fluoride, that's a lot of negative charge. That's all kind of, you've really increased the negative charge relatively. And so there's just a lot of additional negative charge. It's very concentrated. All those electrons are very close together, meaning that this is relatively unstable, and it's going to attract an H plus in order to become more stable. So anything that is a large atom that we're, bonded into a hydrogen, that tends to be a pretty strong base, or a relatively stronger base than something that is smaller here. If we turn to the periods on the periodic table, we can also find predictable trends. So say, for example, CH4, NH3, H2O, HF. So in all of these cases, carbon, nitrogen, oxygen, fluorine are in the same period on the periodic table. And as you move from left to right, acid strength increases. So we can even understand that in just like how we talk about this. The name of this molecule is hydrofluoric acid. It's the only one that has acid in the name because it's the strongest among them. And basically the reason is, right, previously we said that atomic size, relative atomic sizes had really informed relative strength of bonds. All of these are all similar sized atoms. So these bonds actually all have similar strengths. And so how we understand this trend then is based around electronegativity. We know that electronegativity informs the sharing of electrons in a bond. Hydrogen is the same here, but as you go from carbon to nitrogen to oxygen to fluorine, your electronegativity is increasing. And what that means is that when you have these really high electronegativity differences, HF is a really high electronegativity difference. Basically what that means is that the fluorine is slightly negative and the hydrogen is the fluorine is slightly negative and the hydrogen is then slightly positive. So you have this slightly positive side of the on the hydrogen. That's very similar to, the H plus that you would lose as an acid to a base. So what functionally happens is that these molecules are more attractive to bases, which are looking for those H pluses. And so we have these maps that are down here for CH4, NH3, and H2O of showing the relative kind of enrichment or depletion of electrons. We can see that CH4, this is something that we said never behaved as a base. And you can see that the color green there shows that it's kind of a reasonable or kind of very equal sharing of electrons. This is a nonpolar molecule, very close to equal sharing of electrons, not much in the way of dipoles. As we get to NH3, it increases. We see this red, which corresponds to electron-rich region around the nitrogen. It gets even more extreme. This very dark blue color shows up in water. Water is not a very strong acid, but it is a much better acid than either ammonia or methane, right? Methane, we say, would functionally never lose an H+, whereas water, it's all right at it. It can do it if it needs to. And so we can make these predictions based on where an atom is on the periodic table of if that atom is bonded to a hydrogen, will it be an acidic hydrogen? And so we can use our column rules and we can then use our period rules. I should note that the period rules aren't quite as, the column rules generally you see bigger changes there. Another video down and another video without a participation question, but we got plenty more videos to go. No, we don't. We only have one. There's only one more video left. See if there's any questions in that one. Who knows? We'll see you there.